Okay, let's do a short video here, just kind of talking about independent and mutually exclusive events. So these are not the same, and we're going to kind of discuss these differences, then maybe one or two other topics in probability here. So as I said, they are not the same, and an independent event is independent if the following are true. If the probability of A given B is equal to the probability of A, or the opposite, or if the probability of A and B equals probability of A times probability of B. Sorry, those aren't or, those are and, so all three of those have to be true. Now, two events, A and B, are independent if the knowledge that one occurred does not affect the chance that the other occurs. That is the very key sentence. I underlined it for you. That's kind of your takeaway. For example, the outcomes of two rolls of a fair die are independent events. The outcome on one roll does not change the probability for the outcome on the other. So it doesn't change your sample space, it's just two separate events. Now, a mutually exclusive event is events that occur at the same time. So think of rolling a die and you have evens and odds. You cannot have an even and an odd. They occur at the same time. If probability of A is evens, probability of B is odds, they are mutually exclusive. The probability that they occur together has to be zero. It's one flip. If it was two flips, then that would not be the case. Okay, now sampling with or without replacement. We talked about this in terms of samples. Now we're going to talk about it in terms of population. So it's the same kind of concept. Instead of having, if you have 52 cards and you take one card out, you're going to have 51 cards, and that would be without replacement. And if you're going to do with replacement, it would just be out of 52 every time. So if I want to know the chances that I draw 4 aces in a row, I'm going to have 4 out of 52 for my first draw. If I do it with replacement, I would have 4 out of 52 for my second, 4 out of 52 for my third, 4 out of 52 for my fourth, and it could keep going and going and going. Without replacement, I'm going to have 4 out of 52 for my first draw, 3 out of 51 for my second draw, 2 out of 51 for my third draw, 1 out of 51 for my fourth draw, or out of 48, sorry. And then as we continue on, we'll have zero probability of drawing any more. Right after you draw the 4 aces, there's none left in the deck, so my odds of drawing an ace are 0. So without replacement, you see that the odds of the same occurrence happening start to dwindle because the sample space is, or the amount of possibilities that an ace can be drawn is diminishing. And here's the multiplication rule. We talked about this briefly. Just kind of review again. Probability of A given B is equal to the probability of A and B over the probability of B. So these are, once again, we're just going to be kind of looking at these separately and then combining them just like any other formula, just straightforward algebra. And similarly with the addition rule, so I kind of mentioned this in the previous video. If we have probability of A or B, then we're going to have the probability of A plus the probability of B minus probability of A and B. If A and B are mutually exclusive, they cannot occur together, then probability of A and B here we know is 0. If probability of A or B is flipping a coin, heads or tails, probability of A is 0.5, probability of B is 0.5, and probability of A and B, you cannot have a heads and a tails. So this is 0, which then just leaves you with probability of A plus probability of B. So if A and B are mutually exclusive, then your formula is just this part. but if they are not, you have to include the minus probability of A and B. Doesn't work very well for the heads or tails example, but for, let's say, a die roll, and you want to know the probability that you get. Probability of A is that you roll a 1 or a 2, and probability of B is whether you roll a 2 or a 3. The probability that you of A or B is going to be 2 over 6 plus 2 over 6 minus the overlap, which is 1 over 6. And that's important because otherwise you're going to be double counting that space. I'm going to actually draw this out for you here in terms of a Venn diagram. So, I have a space. We'll get into Venn diagrams a little more, but almost everything that we do in statistics, I'm going to use these. So this is probability of A. This is B. Now, since they overlap, we're saying that they are not mutually exclusive. You can have A occur and have B occur, and that's this space here in the middle. Now, the size of B is a full circle, right? The size of A is a full circle. If I was to add A and B, I would be double counting this space here. So I have to subtract one of them out. So basically the area of this and the area of this is greater than this entire area. So we have to cut that out. And this would be the entire sample space in here. This is all possible outcomes, which would be, in our example, other die rolls. So 1 through 6 is represented in this entire space. Hope that helps. Like I said, I'll be using these a little bit more, and spend some time to kind of visualize this, because this does become very important, understanding why you don't want to double count.